So the last name is Sigurdarson, or Sigurdarson in Icelandic. Does this work?
Yeah.
Testing?
Yeah.
Loud enough? Okay. So this is the iSpace lab as of 20 minutes ago, I think. My name is Salvar. I'm a second-year master's student working in the iSpace lab with Bernard and my colleagues. And I'm going to talk about my research, but I'm also going to kind of bend the rules a little bit because I enjoy doing that, and talk about my motivation as well, for why I'm doing this research. And the story starts in Reykjavik, Iceland, about a year and a half ago, and I live here, and I work here. These are the actual locations. I managed to find a picture that contained both. And I'm working at this air traffic control center developing safety-critical software. And it turns out that developing safety-critical software is not a never-ending roller coaster of fun and games. It's serious business. And serious business tends not to be, really fun and exciting. So I figured I needed a change of pace. And I'm looking through some websites, some options of studying abroad, and I somehow find the SIAT website, and I end up at the iSpace website. And I find it kind of interesting because I'm thinking these guys are doing some virtual reality research, and at the time when I think virtual reality, I think of this or this. I thought it was just some 90s fad that was really, it was supposed to be everything, and then it didn't do what it was supposed to do and died out. And it turned out that it's not true. I mean, it's not as amazing as it was projected to be, but it's an actual field in research and in industry. So it's used for flight simulation. It's used for architectural design. It's used for all kinds of military training purposes. And so I was kind of interested, kind of intrigued. But the moment where I decided that I needed to quit my job, sell everything I owned, hop on a plane to Vancouver and come here was when I was reading a paper that Bernard had sent me that was explaining the process of spatial updating, which is the process that our brain does to keep us oriented as we move around. And I thought this was amazing because it's a process that it's incredibly complex, like many other brain processes, sure, but I found this one really interesting. It's also incredibly important because all of us use it all day, every day, to stay oriented. And yet, most of us never even think of it as a thing. We don't even think about it ever. It just happens effortlessly. We don't even have to worry about it. And it really amazed me because when you think about it, if I turn around fast like this, everything that I used to see is now gone, and everything I'm seeing now has appeared within the last second. But yet I don't think that the world has changed suddenly. I know that I have just rotated 180 degrees in the world because this process just automatically and effortlessly tells me using visual information and other information to tell me that I've just moved in the world. And what I found even more amazing was that you don't even need visuals at all. I can close my eyes, and I can walk, and I can turn. And I know that I came from there. I'm now facing this way. I used to face this way. The screen is there. You're over here. And the most amazing thing about this is that I don't use any visual information to calculate this. All my brain has to go on is information from a tiny bit of water in my inner ear and signals from my muscles and bones. And I found that just completely amazing, so that was enough for me. And then now we get to the research problem. Because as amazing as this process is in the real world, it's not quite as amazing in virtual environments. Because when people that are using virtual environments, if they don't have obvious landmarks to rely on, and especially if they can't, if they don't move physically as they move in the virtual world, they tend to get disoriented and lost quickly. They miscalculate the distances and directions, and this can really be a problem in many uses of virtual reality, because a flight simulator that doesn't give you a sense of movement or direction isn't really good at simulating actual flight. The same with driving simulators and so on. So the obvious question is why? Why does this not work in virtual reality? And an obvious guess is, like I just said, if this particularly happens if you don't get physical motion cues, if you don't get to actually move physically while you move in the virtual environment. And that is the prevailing notion, that you need physical motion cues. You need to actually move. That's what triggers this automatic spatial updating process. So you can't just use visuals alone. But one problem with the studies that found this truth was that almost all of them used a visual of a type called optic flow, which is basically just a moving visual field with no landmarks and no discernible anything really. It looks like this, or like a star field. So as you move through it in the virtual world, you sense that you're moving, but there's no other information. You just move through this star field and you see things moving past you, and that's all you have. So that motivated Bernard and colleagues to do studies in 2006 and 2007 to further investigate this and find out whether it would make a difference if the visuals were more realistic. And so they used photorealistic replicas of real environments, in this case a town square in Tübingen, in Germany, and had participants rotate visually in the virtual environment and point to different targets that they couldn't see after being rotated, but they had seen before they rotated, and thus measuring how well they were oriented after they moved. And they found that with visuals like these, they could in fact trigger automatic spatial updating without having to physically rotate participants. Now there's one, and this was an interesting finding and went kind of against the prevailing notion in the field. Now, there's one limitation with this study, is that they only looked at rotation. So they had people sit and rotate virtually and then point to different targets. What they didn't do was add translations, where they had people actually move and rotate through the virtual environment and then point to different targets. And that's where my study comes in. So I want to build on this work and further investigate this by adding the translations to see what happens if you actually move through an environment and rotate, and when it's highly detailed visuals. So the research question became, when moving along a path in a virtual city with naturalistic and highly structured visuals, are physical rotations still needed to enable automatic spatial updating, or can the visuals alone suffice? And for this, we used the amazing motion simulator that we recently built in the iSpace lab that Bernard just showed you. And after doing some programming to allow us to rotate it with software, and some more programming to build a virtual city, we had people sit in a chair with a head-mounted display that showed them the environment. And we had them go down different paths with different curves in different directions. And each of the trial had them move passively down the path, and they could look around if they wanted with head tracking. And at the end of the path, they were asked to point back to the origin, the place where they thought they started, as quickly and accurately as possible. They didn't see this arrow, it's just to show how they would point back. And the idea with this is called the point-to-origin paradigm. And the idea is that by measuring the pointing error, you can pretty accurately measure how well you are oriented in space whether it's real or virtual. And what we, to answer the question, the research question, we had two conditions. One, where they only watched this movement visually, they only saw it, there was no physical movement. In the other, they physically rotated on the treadmill, on the motion simulator, as they rotated in the virtual environment at the same speed and same acceleration. So we were trying to see what effect did adding the physical motion cues, what effect did that have? Did that allow them to point better? Did that improve it? Or what did it do? And in short, just in the interest of simplicity and time, we got some more results, but the main result was that it didn't do anything. It didn't help them point more accurately or more quickly. It had no effect. And why, we asked, and we're still asking that, actually. And there are two possible explanations. One is that this is a kind of a ceiling effect, which means that the visuals alone were good enough that they triggered automatic spatial updating, and the physical motion cues, they couldn't improve anything. There was nothing to improve, which is what we hope to be the case, but we can't know for sure. Because it could also be a sort of floor effect, I guess, meaning that none of it helped. The visuals didn't trigger automatic spatial updating, and for some reason, the physical motion cues didn't either, which is unlikely because the literature has a bunch of studies showing that adding physical motions does help in triggering automatic spatial updating, but we can't know for sure. And so the next steps we have are to run a follow-up study where we add a condition where we change the quality of the visuals. So we would have them do a similar task in one case in a virtual environment like the one I showed you, and then another task, a similar task, but in a optic flow environment, just a star field where they just move and turn and they don't see any streets or they don't have the highly structured visuals. And hopefully with data from that, we could pull apart better the role of the visuals and the physical motion cues and find out who's the real hero. And so to conclude, there's the obvious who cares question. Why does this matter? Who cares about this? And Bernard kind of mentioned this in his introduction, but it's basically, this is pure research because we're finding more about the brain, how the brain represents space as we move. And knowing more about that is good because pure research is knowledge for the sake of knowledge. There's also applied research because knowing more about how we trigger automatic spatial updating in virtual environments can allow us to make better virtual reality simulators, which can better teach people how to fly and better train people how to drive or better train people how to perform surgery, just for a few examples. But there's also, the applied stuff also feeds into the pure part because better virtual environments, better virtual reality simulators can allow us to run better psychology experiments. Just like Bernard said, virtual reality is a really good experimental tool in psychology. And so we can run better experiments that tell us even more about how the brain works. And it feeds back into, it becomes a loop when knowing more about the brain can allow us to make even better virtual reality simulators. And this feeds into this loop. And that's who cares, and that's my research. Thank you. Questions? Yes?
The movement in these experiments was generated by the equipment, not by the participants?
Yes. Repeating the question, so you're asking whether the movement was active or passive, I'm guessing. It was passive. They did not control their movement themselves.
Does it make a difference if we're active?
Yes, but I'm not sure how. It definitely can. And we are doing, I know Daniel is doing experiments that involve active movement, where they control themselves either by using a joystick or the chair itself, which he will show you in his talk later. So, yes?
Could you show the animation of how of the experiment?
Yes, can I show the animation of the experiment? There. So this is just one trial. This is a 10-degree turn to the left. And so we had 10 degrees, 50 degrees, 90 degrees, 130 degrees, and 170 degrees in either direction. So the 10 different trials, which we ran many times. And each of them were the same. They started out at the starting point, they were moved passively down the street, then they stopped at the end and asked, there was a sound, a bing that instructed them to point back to the origin. And we recorded all kinds of data where they pointed compared to where they were facing and how quickly they pointed. And we also had some qualitative, like we had them rate how difficult it was to point and so on.
I'm not sure whether my question makes sense, but if you would run this experiment in a physical setup where someone was in a car in a similar city, would you expect them to perform? Would you expect to see similar results?
That's a good question, and that's one reason that virtual reality is really good, because it's really hard to build an actual city to run a psychology experiment, and so that would be really interesting. It would be awesome if we could do that, but it has limitations in practicality, I guess. But yes, it would be very. I'm not sure. I would guess. I mean, in that case, there's no virtual anything. So all the natural processes get activated just as as they do every day. So, but would the performance be better? I'm not sure. Yes.
The question about the field of view, what's the visual angle that this subtends of the slice of sense?
Yes, what's the field of view? Sorry? 32 by 24.
Visual angle is, it looks like it's only about...
Yes, it's limited.
Yeah. So
We-
do you think that if you did this where they had a more wide field of view that sort of corresponded to what's called our useful field of view in the real world, that your results would be substantively different?
They could be.
Because this window painting, we do know, has an effect on people's perception of motion. I don't know about self-motion, but the window painting, not the window painting, but this sort of tunneling has a big effect on how people stitch together motion
Yes, for
cues
sure.
in the environment.
Yes. We do have a new head-mounted display in the lab, which has a much wider field of view, and it also makes people much more nauseous, which is kind of a downside. It's like a very it's the elephant in the room for virtual reality, I guess. But that's definitely something we can also investigate.
So we can say people were already surprisingly good, so we are probably already at a ceiling level, even with such a small field of view.
Thank you.